Hi, I'm Jaeyoung from KAIST. In this video, I'm going to talk about neural-enhanced live streaming, improving live video ingest via online learning. Live video traffic has experienced a rapid growth with the rise of live streaming services such as YouTube Live, Twitch.tv, and Facebook Live. According to the market report, the live video traffic will increase 15-fold and take up 17% of internet video traffic by 2022. With the number of streamers and viewers on the fast rise, supporting high-quality live streaming has become ever more critical. Live streaming systems consist of two main components. First, the ingest side concerns the delivery of live video from original streamer to a media server. When the streamer uploads a high-quality live video to the media server transcodes the ingest stream into video chunks with multiple different qualities. Second, at the distribution side, content distribution servers use adaptive bitrate streaming to optimize the quality of experience and scale across thousands of concurrent viewers. However, there still exist key limitations in an end-to-end live video delivery. The stream quality is fundamentally constrained by the streamer's uplink bandwidth and its computational capacity. For example, if the network bandwidth between the streamer and the media server is scarce, or if the streamer lacks computing power on their devices to encode live stream in real time, the ingest stream quality suffers by limiting the transcoded options and restricts the quality of the entire delivery downstream. This potentially deprives thousands of viewers of their opportunity to enjoy high-quality live stream. Therefore, in this work, we focus on the first hop delivery between the streamer and the media server, namely the ingest. We propose a new live ingest framework called the LiveNAS that aims to enhance the video quality of origin stream at ingest. Recent advances in neural-enhanced video delivery present a unique opportunity to enhance the video quality by applying DNN-based super resolution on video frames. Leveraging the great benefit of DNN-based super resolution, NAS shows that super resolution enhances video quality independent to network bandwidth. It uses the client computation and applies super resolution DNNs to the downloaded chunks. Inspired by the previous work, we ask ourselves, can the similar benefit of super resolution be applied to the live streaming context? And our answer is LiveNAS. By leveraging the computing power at the ingest server, we can apply super resolution on the original ingest stream at the ingest side before its distribution to the end viewers. Since the high-quality video is now available at the media server, this enables thousands of viewers to download high-quality live stream if they have enough bandwidth themselves. Moreover, super resolution is expected to provide much more benefit at the ingest than it does at the distribution. Let me show you the figure that compares the bandwidth used between WebRTC and Dash. WebRTC is a de facto standard for live ingest, and Dash is a de facto standard for adaptive streaming. We can notice that live streaming uses the bandwidth more conservatively. This is because, first, the ingest client must avoid packet loss to minimize the latency due to retransmission. And second, unlike adaptive streaming, ingest servers cannot use buffer to observe the network changes. Fortunately, when you apply super resolution at live ingest, it provides benefit comparable to having almost 2 times of the bandwidth. This is greater benefit considering the NAS provides benefit comparable to having 17% more bandwidth. Therefore, the benefit of super resolution is even more attractive in live streaming. However, there are two primary challenges of applying super resolution in live streaming. First, content-aware DNNs cannot be prepared on the fly for the new live content. In DNN-based super-resolution, it is known that super-resolution DNN provides great benefit when trained and used on the same content, namely content-aware approach. In fact, to prepare the content-aware DNN for per video, it requires 10 minutes of training for a 1 minute of video. The approach cannot be easily adapted to the live video delivery, considering its stringent delay requirement. In addition, pre-training a DNN to a video from past live sessions cannot deliver reliable quality gain compared to the content-aware DNNs. This is because the live content can be very new and different from history sessions. To address the challenge, our solution is to employ online training with fresh data while live streaming. Second, to train the DNN online, it requires powerful computing devices, but the computing power at the streamer side is heterogeneous. Instead, we can leverage the computing power at the Ingest server, which is typically a cloud environment with ample computing resource. However, the challenge is that ground truth labels for online training are not available at media server. To address the challenge, we rely on our key observation that even a fraction of ground truth labels can provide substantial training gains. Leveraging this, our solution is that streamer sends fractional training data to the ingest server. To explain in detail, LiveNAS operates both at the streamer and the server side. At the streamer side, the camera captures the high-quality stream before its compression, and LiveNAS samples partial high-resolution data, which is used for training. Then, the streamer sends sampled training data patches along with the compressed live video frames. At the media server, the online training and inference operate in parallel. The online training learns new features of a video stream online with received patches from the streamer and updates the freshly trained DNN to super resolution processor. The online training approach, however, involves solving non-trivial challenges. First, the high-quality patches that a client transmits share the ingest side bandwidth with live video. Allocating large bandwidth for training patches can improve super resolution. However, it leaves less bandwidth for live video, which can cause quality degradation. To address the challenge, we introduced the quality optimizing scheduler that effectively balances the allocation of uplink bandwidth between training patches and live video. Second, ingest server must support large number of streams. For example, there are average 90,000 concurrent streams on Twitch. If we naively dedicate one GPU for online training to each stream for the entire stream duration, LiveNAS can only provide benefit of online training to the limited number of concurrent streams. Therefore, efficient resource use for online training is required. To address the challenge, we introduced the Content Adaptive Trainer. Now, let's look at these two design components in detail. The goal of Quality Optimizing Scheduler is to allocate bandwidth use between video and training patches that results in maximum video quality. The optimization goal is expressed as a sum of video quality and the future discounted quality gain due to online training. We observe that optimization objective is concave function. First, the video quality function is concave as video quality with regard to the bit rate is concave. Second, the DNN quality function is also concave because it monotonically increases with respect to increase in the training set, yet the marginal improvement diminishes. Since any linear combination of concave functions is concave, our optimization objective is concave function. This allows us to apply gradient ascent approach. Therefore, our quality optimizing scheduler applies gradient ascent to find patch bitrate that leads to maximum video quality. The scheduler takes measurement of video quality, DNN quality improvement, and the estimate of available bandwidth from the transport layer. Then it updates the target bitrate of patch, video, respectively. The goal of Content Adaptive Trainer is to improve the resource efficiency of the online training. Our observation shows that for videos with minimal scene change, the online training gain eventually saturates to the point where further training may not provide benefit. However, when a new content appears, the online trained DNNs cannot keep up with the scene change, and therefore it needs additional training. Thus, real-time adaptation to the content can improve the resource efficiency. Our Content Adaptive Trainer suspends the training when it detects the saturation in the training gain and resumes training when it detects the scene or content change. In this way, LiveNAS is able to adapt the amount of training time to the real-time quality gain. So far, we've talked about two main design components. Additionally, there are two remaining components in LiveNAS that deals with selection of training data and real-time super resolution. One of them is a patch sampler, which operates at the streamer side and selects the high-quality labels to be transmitted. It preferentially selects the ones that make training gain to appear as large as possible by including the patches that are more difficult to encode. This is because the patches that are more difficult to encode have room for more improvement. The other is Super Resolution Processor, which operates at the server side and enables the real-time super resolution up to 4K resolutions. For example, in case for the 4K super resolution, the processor splits up the original ingest image into 3 equal pieces and then individually apply super resolution using 3 GPUs. Then the outputs are stitched back to produce 4K image. This takes 29 milliseconds per frame, which translates to 34 FPS. Putting the design components all together, here is the overview of LiveNAS system. LiveNAS is implemented on top of the state-of-the-art open-source Ingest framework, WebRTC. We implemented LiveNAS server and client in Python to utilize PyTorch framework and use the Python C++ wrapper to integrate LiveNAS and WebRTC. Besides the WebRTC, LiveNAS design components can be implemented on top of any ingest framework since it is agnostic to video codec and transport layer. We now evaluate LiveNAS by answering 3 questions. First, we show how much video quality improvement LiveNAS can deliver under a constrained environment. Second, we show how effective is content adaptive online learning in terms of the resource efficiency. Finally, we show the impact of the ingest improvement of LiveNAS on the distribution side. Our evaluation consists over 300 hours of live stream using the real network traces collected from 2019 FCC broadband. We used total 9 video contents, which consist of top 5 contents from Twitch and 4 popular contents from YouTube. For the super resolution DNN model, we used the ultra-high model from NAS. We chose the ingest resolution following the YouTube live settings, and target resolutions are 1080p and 4K for Twitch and YouTube contents respectively. Before presenting the results, I would like to show you a demo. In this demo, it shows the actual recorded live stream of 2 most popular contents on Twitch. The left half is what WebRTC delivers under a network-constrained environment, and the right half is what LiveNAS delivers under the same environment. You can see that video is much clearer in LiveNAS. Next, I'll show how much video quality improvement LiveNAS delivers. To quantify the video quality improvement, we use PSNR, which is a widely used metric for video quality. We compare LiveNAS with 3 baselines. First baseline is WebRTC, which does not utilize DNNs, but uses bilinear interpolation to scale up to target resolution. Second baseline is generic DNN, which uses a super resolution DNN trained on a standard benchmark dataset. The last baseline is pre-trained DNN, which uses a prior stream, if available, from the same streamer to pre-train the model. Left-hand side presents the result of 5 Twitch contents, and x-axis is the content name. Right-hand side presents the result of 4 YouTube contents. The result shows that LiveNAS outperforms both WebRTC and generic DNN baselines. For the Twitch contents, LiveNAS outperforms the pre-trained model except for the Fortnite content, whose quality was nearly the same as pre-trained. However, this result only appears when the best trained data is carefully selected from the prior stream. Overall, LiveNAS outperforms WebRTC by average 1.96 dB and generic super resolution by average 1.19 dB in PSNR. We now show you how much research the content adaptive learning can save. Here, the figure shows the actual GPU usage time for online training compared to the stream length. On average, LiveNAS performs online learning for only 25% of the streaming time. To see how effective the content adaptive learning is, we compare LiveNAS and WebRTC with 2 baseline training methods in terms of resulting video quality. First baseline is the one-time customization, which trains DNN upfront on the first few seconds of the stream and never resumes even when scene or content changes. Second baseline is continuous online training, which trains DNN continuously without any suspension. The training time is identical to the stream length. LiveNAS delivers almost the same quality while using 25% of GPU resources compared to the continuous training. One-time customization, however, comes at a significant decrease in quality because it does not keep up with scene change. When we quantify the computation cost for LiveNAS, the average cost is around $4.7 per hour per stream on Google Cloud. Finally, we show you the impact of LiveNAS on the distribution side. To quantify this, we measure the QE of viewers at the distribution side. We used pensive and robust MPC as an adaptive bitrate algorithm and simulated adaptive streaming on 2 traces. One is the downlink traces from FCC broadband, and the other is the traces from pensive. Overall, LiveNAS Ingest delivers 12 to 69% improvement in average QoE on the distribution side. The improvement comes from 2 reasons. First, LiveNAS provides higher resolution chunks benefiting viewers who have ample bandwidth. Second, each encoded chunk is of better quality because ingest video quality improves with LiveNAS. In many cases, the improvement LiveNAS gives is much larger than what the advanced ABR algorithm produces. For example, pensive's improvement over robust MPC is 13% for Twitch video, but LiveNAS gives 27% improvement over WebRTC ingest on the same traces. This implies that in live streaming, ingest side improvement is crucial, and it is as important as ABR algorithms for enhancing the QoE of end viewers. To sum up, I have talked about 3 things in this talk. First, LiveNAS is a new live video ingest framework that enhances the original stream's quality via online learning. Second, LiveNAS introduces novel design components including quality optimizing scheduler and content adaptive trainer. Finally, LiveNAS produces significant QoE improvement for live stream viewers. More information can be found in our website. Thank you for your attention, and if you have any questions, I'll be happy to take them during live Q&A session at the conference.